Torque on a dipole. An electric dipole with dipole moment P is in a uniform external electric field E. Part A. Find the orientations of the dipole for which the torque on the dipole is zero. Part B. Which of the orientations in Part A is stable and which is unstable? Consider a small rotation away from the equilibrium position and see what happens. And part C, show that for the stable orientation in part B, the dipole's own electric field tends to oppose the external field. Okay, so first of all, what is an electric dipole? We have a charge minus q and another point charge plus q separated by a distance d. The electric dipole moment vector points from minus q to plus q, you can see here in this direction. And we have a uniform electric field E, which makes an angle theta with the dipole moment vector. And this is our x-axis, y-axis, and z-axis. So this implies that under the influence of this uniform electric field, this plus q feels an electrical force q times the electric field in this direction, parallel to the electric field. Minus q feels an electrical force q times electric field in a direction that opposes the electric field because of the negative charge. Okay, so first of all, we have the electric dipole moment vector according to this figure is the charge q multiplied by the distance between the charges pointing in I hat direction because it points from the negative charge to positive charge. The electric field has two components. Electric field is equal to E cosine theta I hat plus E sine theta j hat. So you can see its components here, cosine theta I hat, sine theta j hat. So that means there is going to be a torque due to this electric force around the center point here, the pivot point here. That torque we can calculate to be the force QE perpendicular component sine theta multiplied by the distance with respect to the pivot point. The pivot point is point O, the center. The point of application of the force is at a distance d over 2, and we just looked at the perpendicular component of the force. So this is R cross F, QE sine theta d over 2. And what is the sense of rotation here? The right-hand rule shows us go from the pivot point to the center, to the point of application of the force with 4 fingers of the right hand. Curl your fingers towards the direction of the force. The thumb points out of the board in plus k hat direction, as you can see here. So this is in plus k hat direction. And how about the torque due to this force? This is going to be QE sine theta, and the perpendicular distance between this force and the pivot point is d over 2. Using the right-hand rule, the 4 points point from point O to minus q. We curl them towards the force, and the thumb points out of the board again. So the sense of rotation here, according to this torque, is in this direction and also in this direction. As you can see, both are counterclockwise, giving us a positive torque. So this is plus QE sine theta d over 2 in k hat direction as well. All right, and now what is the net torque? The net torque is then, because I have twice the same quantity and this is d over 2, it will become d. So it is q d multiplied with E sine theta in k hat direction, which is something we recognize. It's the cross product of the p vector with E vector. Now, p vector is this vector that points from minus q to plus q. E vector is this vector. Cross product p cross E is in plus k hat direction, and the magnitude of p was qd, so it is qd E sine theta, which is P cross E. All right. Now, when is this torque equal to 0? Torque equals P cross E. This is going to be 0 when you have P multiplied with E, sine of the angle between them, theta, equals to 0. So this tells us that sine theta should be equal to 0. So we obtain 0 torque for theta is equal to 0 or theta is equal to pi. So the 0 torque configurations are theta equals 0 or theta equals pi. If we draw this, theta equals 0, the P vector is aligned with the electric field vector, or P vector is anti-aligned with the electric field vector. So we see that the torque on a dipole is 0 when it is aligned or anti-aligned with the electric field. Now, we're going to look at the stability of theta equals 0 and theta equals pi. In part B, we consider a small perturbation from the equilibrium position and see what happens. Small perturbation by an angle delta theta. Let's look at what happens in this scenario. So the electric field and the dipole moment vectors were aligned. Now we have a small perturbation. Now P cross E, using the right-hand rule, 4 fingers point in the direction of P, curl them towards E, the thumb points into the board. It's in minus k hat direction, giving us a sense of rotation that is clockwise. All right, so the torque that is P cross E is P E sine of the angle between them, delta theta, in minus k hat direction. So what is this doing? It is restoring, it's a restoring torque, torque. Therefore, when you disturb the system from its equilibrium position, it tries to go back to the equilibrium position. Therefore, this is a stable configuration. If I have the P vector and E vector anti-aligned, now you can see the direction of the torque is P cross E, 4 fingers point in the direction of P vector, curl them towards E, it's in k hat direction. The sense of rotation is counterclockwise, so it tries to open up this angle even more. The vector between the dipole moment vector P and E here is pi minus delta theta. So you can see that the angle between the P vector and the electric field vector is pi minus delta theta, and the torque that is P cross with E is going to be P E sine of pi minus delta theta in k hat direction. And what is sine of pi minus delta theta? This is equal to P E sine pi cosine theta minus P cosine delta theta minus PE sine of delta theta cosine pi in k hat direction. Sine of pi is equal to 0, so this is going to disappear, it's 0. So we obtain cosine pi is minus 1, so this will give me PE sine delta theta in k hat direction. So what does this tell me? The sense of rotation is counterclockwise. It tries to open up the angle even more. So what we see is that we have a runaway from anti-aligned position. Therefore, we can conclude that the equilibrium we obtain in the anti-aligned configuration is unstable equilibrium. All right. So that's the answer to part B. Which orientation is stable? The aligned orientation is stable and the anti-aligned orientation is unstable. So this is aligned orientation is stable and anti-aligned orientation is unstable. Anti-aligned orientation is unstable. All right, part C, show that for the stable orientation in part B, the dipole's own electric field tends to oppose the external field. Okay, so now, what is the direction of the electric dipole moment vector, P, pointing from minus Q to plus Q? It is aligned with the electric field. That's the stable configuration. What is the electric field due to this dipole? It points from plus Q to minus Q, plus Q to minus Q, plus Q to minus Q. You can see that the field lines are going to be going from plus Q to minus Q. So electric field due to the dipole, the field lines indicate that the E dipole is going to oppose the external electric field. So as suggested in part C, the dipole's own electric field tends to oppose the external electric field. It is going to be pointing from plus Q to minus Q, but the electric external field is parallel to the P vector, which is pointing from minus Q to plus Q. So this is our conclusion. E dipole opposes the electric field. So in this problem, we looked at an electric dipole. The dipole moment vector points from minus Q to plus Q. In this direction, when electric field, a uniform electric field makes an angle theta, which is with respect to this dipole moment vector, whose magnitude is the charge multiplied by the distance between the charges, actually. This is going to introduce a torque. It's going to have a torque effect on plus Q and minus Q with respect to the center point O. And we have seen that this torque is equal to 0 when the angle between the electric field and P vector theta is either 0 or pi, or it's either aligned or anti-aligned. If we consider a small perturbation about this equilibrium position for the aligned configuration, we see that the torque P cross E basically tries to restore the equilibrium position. So it tries to go back to the equilibrium position. Therefore, this equilibrium is stable. Here, on the other hand, for the anti-aligned configuration, P cross E causes a sense of rotation which is a runaway. It's trying to increase the angle delta theta, therefore is an unstable configuration. And for the stable configuration, the dipole field pointing from plus Q to minus Q opposes the electric dipole moment vector P pointing from minus Q to plus Q, which is aligned with the electric field for the stable configuration. Therefore, we see that the field lines indicate E dipole opposes this electric field. So it's going to be this is going to be the result for the stable configuration.